Hello everyone, this is our last week of doing new material. We're going to cover the fundamental theorem of calculus and how to apply it, and we're also going to cover the method of substitution. So those are the two things we need to finish this week, and then next week we'll have test 3. On Tuesday we'll have test 3, and I'm going to put more information about that online and some notes on Moodle. I'm also going to do a practice test because this is going to be take home, so it's going to be very conceptually based. You're going to have to explain, you're going to have to show work and answer questions that are really going to force you to reason about derivatives and second derivatives and integrals. So I want you to be prepared for that. So I am going to post a practice test. Okay, and then the week after that we have the final exam, which again will be very conceptual. Okay, today we need to do the fundamental theorem of calculus. I'm also going to, before Thursday, post a video on the method of substitution so we can get that off our plate, and I'll assign you homework and so forth. All right, today the fundamental theorem of calculus. In order to understand this, we've got to go back to our graph of velocity versus time, hours. Remember that? We did 50 miles per hour for the first 3 hours, and then for the next 2 hours we did 30 miles per hour. And we said the distance traveled is the area under these velocities. So the distance traveled in the first 3 hours was 150 miles, because it's 3 hours, 50 miles per hour. For the second 2 hour, for the next 2 hours, we went 30 miles per hour. So the total distance traveled, the area under the curve, was 2 times 30, which is 60. So now we translated this in the last set of notes to, and these kind of things are going to be important because I can ask you these kinds of things on the test 3 and on the final too, because it's more a conceptual understanding of it, not just cranking it out. If we do distance versus time, we said, well, for the first 3 hours we're traveling 50 miles per hour, so our function for the first 3 hours, right, is f of x equals 50x. So for the first 3 hours we're traveling 50 miles per hour, so our distance at any time is number of hours times 50. Okay, now on the next part we're going a little bit more slowly, and it turns out that the function on that part of the trip is going to be, we're going 30 miles per hour, so it's going to be 30x plus 60. So if I put in 3, I get 90 plus 60, which is 150, which is where I should be. If I put in a 5, so here at 3 hours I'm at a distance of 150. If I put in a 5 in here, at 5 hours I'm at a distance of 210. So you can see that for this function, from x equal to 3 to x equal to 5, I'm following this function. This is the antiderivative. This is one of the antiderivatives. They differ only by this constant of this function. This is the antiderivative of that function, the function that's just y equals 50. Here the function that's just y equals 30. The antiderivative is 50x for the first one, 30x plus 60 for the second one. How do I, using this function, How do I get how many miles are traveled? I have to put in f at 5 and subtract f at 3, and I get 210 minus 150, which is 60. Well, heck, it's easier to get it off this, right? But that's not always going to be the case. So what I'm showing you here is the idea that the integral, this is the, when we look at the area under the curve, we're looking at the integral of this function. And to get the integral, we can either, if we can, calculate directly the area under the curve. If we can't, we get the antiderivative and look at the difference at the endpoints of the interval we're interested in. So that's what the fundamental theorem of calculus part 2 says. If I have a function like, let's take x squared minus 3x plus 1. Okay, so that's our function. I'm just checking on something. That's our function. So x squared minus 3x plus 1. Let's say we want to know the area under the curve. The area under this curve we want to know the area under the curve from x equal to 1 to x equals 4. So if this is actually the velocity we're going, this is the velocity we're going, we're going to get the area under the curve, which is how many miles we've accrued during that time. So the way we write it is the integral from 1 to 4, and then this is a differential. It tells us what the variable is. X is the variable. Okay, so how do I do that? I get the antiderivative of this, which is going to be x cubed over 3 minus 3x squared over 2 plus x plus some constant. Let's keep the constant. And so this is the antiderivative of that. And we're going to evaluate this at the endpoints. We're going to evaluate it at 4. This is just what we did before. Evaluate it at 4. Evaluate it at 1 and take the difference. So I'm going to put a 4 into this. I'm going to use my calculator. And I'm going to put a 4 into this and a 1 into it, and I'm going to see what I get. So what it looks like what I get is 4/3. When I put in a 4 in here, I get 4/3 plus c. When I put in a 1, I get, so I have 1/3 minus 3/2 plus 1, and I get minus 1/6 plus c. So this is what I'm doing the same thing I just did for our velocity and distance. I'm getting the antiderivative of this. I want the area under the curve for this. I get the antiderivative. Once I get the antiderivative, I put in the 1 and the 4, and I take the difference. Okay, so when I take the difference, it's going to be 4/3 plus 1/6. I got to distribute the negative, minus c. Well, we're going to have a plus c and a minus c, so the constant is irrelevant. It goes away. We don't have to worry about that. But now we've got 4/3 minus a negative 1/6, which is going to be plus 1/6. So that's going to give us a 3/2, 1.5. So the area under this curve from 1 to 4 is 1.5. Now, you can also check this on your calculator. Your calculator, if you put in the original function, which is x squared minus 3x plus 1, and you look at second calc and go to 7, which looks like an integral, and you put the lower limit to be 1 and the upper limit to be 4, you will get 1.5, and it'll even shade it in for you, exactly the area under the curve. Now when you look at this, so when you graph this, if you look at this from say 0 to 4, let's say I'm looking at a good window. When I graph this, 1, 2, 3, 4, it looks like this. It looks like it's going down and then up like that. So it looks like it's doing something like this. So the area from 1 to 4 is this area here. It's this area below the curve and this area above the curve. And what we'll see is the area above the curve is a positive area. You can say, well, this is really small. The area above the curve is a positive area. The area below the curve is usually the area is given a negative. So when you put these two areas together, the negative and the positive, sometimes they sum to 0. For instance, if you take the sine curve and integrate it from 0 to 2 pi, if you take the integral of the sine from 0 to 2 pi, you'll get 0. Why? Because this positive area will cancel out this lower negative area. So it makes sense that this is a small number, because the area below and the area above are two different signs, SIGNs. We'll look at some examples of that. Let's do another simple example just to get started. What if we have something like, and I'm going to call this f of x. I'm going to say f of x is the integral from 1 to x of t cubed dt. So we want to take the integral of this. Okay, so we would have t to the 4th over 4, that's the antiderivative, and we would want to evaluate it from 1 to x. Notice I'm not going to even bother with the constant anymore because it just subtracts out. So I would put an x in here for t and a 1 in here for t. So there's the integral. I didn't get a regular number. Instead, the upper limit is just an x. It's not a 2 or an 8 or a 4. It's just an x. But that's okay, we can still handle it. Now notice, if I take the derivative of this, 4 times x to the 4th over 4, decrease the exponent by 1, I get x cubed. The derivative of this is 0. So notice, when I'm given an integral, and I take an integral like this, where the upper bound is some variable value x, all I get is this same function back with an x instead of a t. So when I take the derivative of this, remember, this inside is the derivative of that. Basically, this is what part 1 of the fundamental theorem of calculus is stating. And basically, that inside it is the derivative of that. Okay, so let's look at a couple of problems. So let's say I'm going to assign, how about number 8. Number 8 from chapter 4.3. So in number 8, it says, use part 1 of the fundamental theorem of calculus to find the derivative of the function. So here's the function. Integral of 1 to x cosine of t squared dt. Okay, and I want g prime. Well, the derivative is just going to be that function inside. That's what that's what part 1 of the fundamental theorem of calculus says. The derivative of this is just the inside function. Remember, when we had a derivative, like the velocity, and the integral was going back to some antiderivative. So this is just part 1 of the fundamental theorem of calculus is just saying again, the derivative and the antiderivative, the integral and the derivative are inverses of each other. Okay. So now let's look at something else. Like, let's do chapter 4.3 number, how about we do 22? So 22 says evaluate the integral. The integral from 0 to 1 of 1 minus 8v cubed plus 6v to the 7. dv. So v is our variable. 1 minus 8v cubed plus 16v to the 7th. Okay. So we're getting the area under that curve. Okay. So all we do is get the antiderivative, which is going to be v minus 8v to the 4th over 4 plus 6v to the 8th over 8. And we're going to evaluate that from 0 to 1. Okay, so I have to put in, we can simplify it. Well, let's not. I put in a 1 here, I get 1. Put in a 1 here, I get 8 over 4, which is just 2, right? Put in a 1 here, I get 6 over 8, which is the same as 3 over 4, right? So that's, I put in a 1. Now I have to subtract off what I get when I put in a 0. Well, when I put in a 0 there, I'm just going to get 0. So what's my answer? 1 minus 2 is negative 1, plus 3/4 is going to be negative 1/4. Notice my answer is negative. So either everything from 0 to 1 for this is under the x-axis, it's a negative area, or we have a negative and a positive area where the negative area is a little bit bigger. Okay, you'll see your assignment in the notes on Moodle for this chapter. Please, if you want more help understanding this, just say, I'd like a conference. I'd like to talk. And I can set up a Zoom and we can talk. Please do that. Bye.